remember what we're talking about here. We're talking about a one-dimensional reservoir. That could be a one-dimensional reservoir in the field, which is thousands of feet long, or it could be a 1D rock core where we do an experiment in the lab. It's the same because we use a dimensionless distance, xd, which is the distance x divided by L. So in either case, it goes from 0 to 1. And this is a plot of water saturation versus distance at some time td. Think of this as being a snapshot in time. And if we were to take the snapshot at different times, the plot would look a little different. But the key properties are that here at x is equal to 0, we have 1 minus SOR. And over here, this is SWR. That's the residual or irreducible water saturation. The key property of this is that we have this in most cases. In most cases, we have the shock front. So the saturation decreases from here to some distance, xd. I'm going to call this saturation at this point SWF. The F stands for front saturation. And then the water saturation decreases abruptly all the way to the irreducible saturation and is over here. And you can think of this as being like a moving wall. So the wall starts at x is equal to 0, and as time goes on, it pushes all the way to the production well at x is equal to 1. And if this was an ideal perfect wall, it would move the oil like a piston. You would inject water and oil would come out at the other end. So 1 barrel of water goes in, 1 barrel of oil comes out. That's an extremely efficient moving wall. That's actually what happens early on. As long as this front hasn't reached the production well, xd is equal to 1, we are producing 100% oil. And this is a very efficient process. So especially in the old days when they did water recovery and they didn't understand the physics as well as we did, they were probably really excited because they would inject, for every barrel of water they would inject, they would produce a barrel of oil early on. And if it were truly a perfect wall, that would occur through the whole time. You would inject water and you would produce oil, 100% of the recoverable oil, not the 1 minus SOR. That SOR will always be trapped due to capillary forces. But you'll produce everything else in 1 pore volume or less than 1 pore volume of water injected. So you would inject water, you produce oil, and that would continue on forever. That would be, well, forever until you run out of oil that you could produce. That would be perfect, but that's not what happens. And the reason is that this wall is sort of like a leaky wall. You can think of it as a wall with holes in it. And because of that, it's leaving behind oil. As that wall is moving, oil gets left behind. And that left behind oil is really this stuff right here. This is unswept oil or bypassed oil. And it's due to the local heterogeneity, the pore scale heterogeneity in the rock, that is manifested in the form of relative permeability curves. So this is oil that's left behind. So as this wall continues to move and it reaches the producer well, once that wall reaches the producer well, we call that breakthrough time. At the breakthrough time, we still have a bunch of recoverable oil that hasn't been produced yet. So at breakthrough time, water that we injected is now being produced. We're still producing oil. We're producing some of this oil that was left behind, but it's not nearly as an efficient process. You might be injecting 1 barrel of water, but you're producing 0.7 barrels of water and 0.3 barrels of oil. And then it gets worse. And eventually it's 95% water, and then it's 99% water. And depending on your economics, at some point it's no longer economically feasible to inject water to produce oil. Now in a reservoir that might take decades to occur, or at least years. But it's something that you need to be aware of. Okay? So that's kind of how it works. And I'll come back to this, but I'll show you what the plot of dimensionless oil recovery is versus dimensionless time. So we're talking about at the producer well, and it's the dimensionless oil. So it's the oil recovered divided by the pore volume. So that can never be greater than 1. And in fact, it can never be greater than 1 minus SOR minus SWR. That's why it doesn't ever get above 0.7. But what's extremely interesting and extremely important is that prior to breakthrough, and this looks like breakthrough right here, there is a straight line between time and oil recovered. And in fact, this is a perfect 45-degree angle. It doesn't look like it because my scales are not quite right, but it is a 45-degree angle. In fact, you can look, if you go up to 0.5, then it corresponds to 0.5. So after a dimensionless time of 0.5, that's 0.5 pore volumes, a half of a pore volume, you've produced 50% of the recoverable oil. That's great. Once you get to this breakthrough, all of a sudden this slope changes dramatically. And then the oil recovery is not nearly as good as you'd like it to be. You're still producing some oil, and at least for part of that time, it's probably economical, but at some point it won't be. But let's derive a formula that describes this, and I'll go back and do again some additional So what I showed here is an example of a saturation front, water saturation versus distance. And I hope that you notice here that this plot looks different than the one I just showed on the document camera. The one on the document camera is more common. It's much more physical. The one I've shown over here only occurs for non-physical relative permeability curves. I did that on purpose because I'm waiting to describe why this shock front occurs. But I could still use this plot to explain what we're talking about now. So this is a plot of water saturation versus distance at different times. Remember, these saturation fronts are saturation or snapshots in time. And if we choose an arbitrary saturation, I chose 0.5 here. I could have chosen 0.4 or 0.7, but chose 0.5. This saturation occurs at a different location, xd, depending on the time. And we say how fast that saturation moves. In other words, the change in distance, x, divided by the change in time, td. We call that the velocity of the saturation front, or dxd dtd. And one thing that we said before is that, okay, so we want a place where the saturation doesn't change, like 0.5. So if the saturation is constant, then that means that dSW, the change in water saturation, is 0. And you may remember from calculus, or you might remember from your thermodynamics class, that we can write a differential that's a function of more than one variable as this. So since SW is a function of both space and time, dSW is dSW dxd dxd plus the partial of SW with respect to TD dTD. And again, we want that to equal to 0. If we divide through by dTD, you get an equation that looks like this. But we recall from a couple lectures ago that we have a PDE that's a water balance that looks like this. So these are two different equations. We've got two different ways. And if we compare them, they look quite similar, except that the one's got this dFW dSW right here. This is the derivative of the fractional flow with respect to saturation. This is the change in distance with respect to time. This is that velocity of the saturation front. And so clearly, for these two equations to both be applicable, dFW dSW must be equal to dxd dTD. And that's what I've written right there. And we can integrate that. And when we integrate that, we did it last time, so you separate your variables, you do the integration. They're very easy integrations, right? So it's the integral of dx and the integral of dt. So then the distance xd is equal to the derivative of the fractional flow times TD. So for a given snapshot in time, right, if we wanted to make one of those plots of SW versus XD, you choose a water saturation SW. Now you'll choose something that's greater than the irreducible water saturation, but an SO that's less than the residual oil saturation. You'll calculate your FW prime at SW. You'll have a plot that you've made. You did it on your last exam, you've done it on your homework. So you use this plot and you calculate FW prime. Then you multiply that by the dimensionless time you chose and compute the distance XD. So if I go back to my plot here, this is SW versus distance. This is my, I'm trying to create this plot here. So what I would do is I would choose a saturation like 0.8. I would choose 0.8 and I would choose this, this is at a given time obviously, so some time TD I've chosen. And at that time, I choose my saturation of 0.8. At 0.8, I calculate FW prime and I multiply it by TD. And what I get is this XD. So I plot this point over here. And then I come plot all my other points and I create this curve. So that's basically how that works. We'll do that maybe as an example problem. Friday might be a good day to do that. Of course, we repeat for other water saturations. And then we do different times so we can create these snapshots at different times. And I should point out, and we'll get to this more later, that at large distances, at distances above the saturation front, the water saturation is simply equal to the initial water saturation. So there's actually some different regions. The first one is what we just showed here. If you're greater than the water saturation, the saturation front, then SW is equal to SWI, right? So if I go back, here, if we're above this distance, then SW is just equal to the initial water saturation. And then SW is equal to 1 minus SOR at x is equal to 0, or technically under this case over here, but that's usually true. So that's why on this plot here, that's why in this plot the saturation starts to decrease immediately. So I'll get back to that point later. So as I mentioned before, these saturations are moving. Once a water saturation that's greater than the initial water saturation reaches the producer well, we call that the breakthrough time. So let's talk about the breakthrough time. We did that a little bit over there. So the breakthrough time is the time at which the saturation front first reaches the producer well. Okay, and the producer well occurs at XD is equal to 1. At the breakthrough time, water begins to be produced, or at least water from the injector. Okay. Now, if we had an initial water saturation that was greater than the irreducible water saturation, we might be producing some connate, some initial water that's there. But what I'm really talking about is the water we injected. So at the breakthrough time, we start producing injected water. And it usually goes from, no water to a significant amount. The water cut, the percentage that's water, can jump very high. Go from 0% to 70% just very quickly. And we'll learn why soon. If we use our equation that XD is equal to FW prime times TD, and we recognize that we are interested in the producer well, where XD is equal to 1, then we can set FW prime times TD is equal to 1. And then the breakthrough time is equal to 1 over FW prime at the waterfront saturation. We're going to learn how to determine the waterfront saturation soon, but remember, it's the saturation at the front. And it never changes, by the way. If you were to plot this at a different time, it might look like this. This is TD2, but SWF is exactly the same. Okay, we'll learn that soon as well. So the breakthrough time, so if you know that this water saturation at the front, which we will, we'll learn how to calculate that. You can calculate the derivative of the fractional flow curve at that saturation, take the inverse, and that gives you the dimensionless breakthrough time. So if FW prime is 2, 1 divided by 2 is 0.5, that means the breakthrough time is half a pore volume. Remember that the breakthrough time will always be less than 1. If you calculate something greater than 1, you must have made a mistake. So again, this is at the production well, and this is the derivative of the fractional flow at a very specific saturation. That's the saturation of the waterfront. As I mentioned, the dimensionless breakthrough time is always less than 1. And again, if SWI is equal to the irreducible water saturation, and in most of the things we'll do in this class, that'll be the case, just to keep things simple, then no water is produced at XD is equal to 1 prior to breakthrough, and 100% is production oil. If SWI is greater than SWR, you will be producing some connate water prior to breakthrough, but you won't be producing any water that you injected. Okay, so then the next thing we did is we started talking about how we can create a curve like this, the dimensionless oil recovery versus dimensionless time. And so that's what we finished up with on Friday. NPD is defined as the oil produced divided by the pore volume. So it is dimensionless, or it's the OOIP, the original oil in place, minus the final oil in place divided by the pore volume. And we showed it's equal to the average water saturation minus the initial water saturation. Okay, so if the average water saturation is equal to the initial water saturation, we produce nothing, right? But SW increases with time as we displace the oil. We also said that we can calculate the oil produced. The numerator there, oil produced, is the integral of the oil rate times dt from 0 to t. Now at early times, QO is going to be constant because we're injecting a constant amount of water. I don't know, 1,000 barrels per day of water, so that means we're producing 1,000 barrels a day of oil. So prior to breakthrough, you produce as much oil as water you injected. But after breakthrough, that oil rate starts to decline. So it is a function of time, and you have to do this integral. And we can remember that the oil rate is just equal to the total rate times the fractional flow of oil. So I've written this as Q times FO, and the pore volume is AL phi. And then I introduce my dimensionless variables, and it gets rid of these constants, and I'm just left with dTd. So NPD is equal to the integral from 0 times whatever dimensionless time I'm interested in, times the fractional flow at a specific location at the producer well, right? That's where we're producing the oil. And it's integrated over dTd. So how do we do this integral? Seems complicated. So let me go back here. I'm going to recall that NPD was SW bar minus SWI. That's more of a definition. But it's also now equal to the integral from 0 to TD of the fractional flow of oil. It's a number between, well, it doesn't have to be between 0 and 1. It could be less than 0 or greater than 1 because of gravity. But in the absence of gravity, it's between 0 and 1. and it's again at a location xd is equal to 1. So at the producer well, and we're going to integrate it over to dTd. So how do we integrate that? Well, we're going to recall from your calculus class, recall integration by parts. The formula for integration by parts is the integral of x dy is equal to the integral of dxy minus the integral of y dx. Okay, or if you learned it like I did, it's a long time ago now, the integral of uv prime is equal to uv minus the integral of vu prime. Okay, so in this analogy, this is the integral of x dy. So this is x, and this is dy. So I can say that NPD is the integral of dxy, so the integral of d FO TD minus the integral y dx. So that's minus the integral of TD dFO. I got to think about my limits of integration. Well, remember we're doing this from 0 to the end of the to the production well. So this is going to go from 0 to xd is equal to 1. And this integral, well, it's got to be dFO, so it's got to have limits of integration of FO. So this is going to go from FOI is equal to 1. So what that means, the fractional flow of oil initially is equal to 1, at least if there's no gravity. And then at a later time, it's something else. So it's the fractional flow of oil at the producer well. Okay. So what do we do with this? Well, this integral is fairly simple. It's, just 1 times that. So what you really get is FO at xd is equal to 1, which is FO at the producer well, times TD. That's that integral. This one's a little bit more tricky. I am going to remember, so I'll put right over here, recall that at the producer, I'll say recall that TD FW prime is equal to XD. And at the producer well, XD is equal to 1. So that means that TD is equal to 1 over FW prime. So if that's the case, I can do this integral as, instead of writing TD, I'll put 1 over FW prime. And since I'm putting this in terms of FW, I don't really like my DFW. So because FO plus FW is 1, DFO is minus DFW. So I'm going to put a negative DFW. And then my limits of integration are not going to be FOI, but FWI now, because I've switched this here. And this will be FW at the producer well. FW prime, I'm going to rewrite that as DFW DSW. And then this DFW can cancel with that. And now I'm left with FOP TD minus the integral from FWI to FWP. This will be a positive because that's a negative and a negative. DSW. Well, that's a really easy integral because this is 1 times DSW. So it's FOP TD plus SW at the producer well minus SWI. I'm going to write that one last time. NPD is FOP, which we just said a moment ago is the same as 1 minus FWP. We know that TD at the producer well is going to be 1 over FW prime at the producer well plus SWP minus SWI. And we also know from before, from up here, that NPD is SW bar, the average water saturation, minus SWI. So if you're done writing that, I'd like to also point out that if this SWI can cancel with that SWI, so if we wanted to know what the average water saturation is, it's 1 minus FWP over FWP prime plus SWP. Somebody might want to know that, but we definitely want to know what NPD versus time is going to look like. And so what are our steps here? So what do we do here? Okay, we want to make a plot. So I'll say plot NPD versus TD. How do we do that? Well, if TD is less than the breakthrough time, if TD is less than the breakthrough time, where the breakthrough time is 1 over FW prime at that front saturation. We don't know it yet, but I'm going to teach you soon how to calculate that front saturation. So you'll know it. You'll go to your FW prime curve. Let's see what that FW prime curve looks like. It might look like this. So if SWF is 0.3, this is over here, you come over here, that looks like 1.3, that's DFW, DSW, and then 1 divided by FW prime, so 1 divided by 1.3 would be your breakthrough time. So if TD is less than the breakthrough time, then it's really simple. Then NPD is just equal to TD. So if TD is 0.1, NPD is 0.1. If TD is 0.2, then NPD is 0.2. All that says is any water we inject at the injector, that's produced oil at the producer. At least that's true if you're at irreducible water saturation. But what if you're greater than the breakthrough time? Else if TD is greater than the breakthrough time. I don't have much room to write here, but I'll try to do it at the bottom here. The first thing you do is, well, you got to use this formula, right? So NPD is 1 minus FWP, FWP prime plus SWP minus SWI. Okay, well that means you need to know SWP, FWP, and FWP prime. Okay, the subscript P stands for production well. So this is at XD is equal to 1, at the producer well. So the first thing you do is you calculate your derivative of the fractional flow at the producer well, FWP, which we know by definition is 1 over TD. Why? Because FW prime times TD is equal to XD, and XD is equal to 1 at the producer well, so FWP prime is 1 over TD. So for any TD greater than the breakthrough time, I take the inverse of that and that gives me FWP prime. So that's good, I got this. I just still need to know FWP and SWP. So B, what do I do? Well, from the curve, well, what did we have? We had this curve here. Okay, yeah. So from this curve here, if I calculate my DFW prime, if it's like right here, then I can come down and I get my SWP. So if this is FWP prime is 1, then SWP is 2, 0.2. So obtain SWP from FW prime plot. Part C, now that I got SWP, I can obtain FWP. All right, this is probably not big enough for you. I'll blow it up. Obtain FWP from FW plot. Okay, so I calculated FW prime at the production well. I use it in the plot to get the water saturation at the production well. Now I can go to my fractional flow curve. Which I know looks like this. And since I know my water saturation, I think I just said it was 0.2 a second ago. Then, as an example, then I come over here and I calculate my fractional flow, my FWP. So now I have FWP prime, SWP, and FWP. Of course, I know my initial water saturation. So now I can get NPD is equal to 1 minus FWP over FWP prime plus SWP minus SWI. So I do that for a bunch of TDs, a bunch of dimensionless times. So go back over here. So prior to breakthrough, this thing right over here, right around 0.6, super simple. Whatever TD is, that's equal to NPD. So at TD is 0.1, NPD is 0.1. When TD is 0.5, NPD is 0.5. But after breakthrough, I've got to follow these steps and calculate the recovery. And unfortunately, it really tapers off quickly. Whereas early on, I'm producing all oil or almost all oil. It's theoretically all oil if I'm at irreducible water saturation. Once I get to that breakthrough, once that water that I'm injecting reaches the producer well, then I'm producing a lot of water. Okay? Still producing oil, so early on you're still making money. Okay, but there is a cost to that, right? So even though you're producing some oil, the water isn't free. It's cheap, but it's not free. The whole process costs money. You need equipment, you need people to be doing this. And then when you produce the oil and water, you got to separate the oil and water, which costs money. So you'd have to do some economics to decide what's the breaking point where this isn't going to work anymore and I need to do something different. drill new wells, do an enhanced oil recovery process, sell the reservoir, you know, something different. Let's go back and see what questions we have. No new questions. It's been a long weekend. Okay. So we got a process for that, but I did want to go and really talk about this shock front and why it occurs and why it happens. So I'm going to ask you to recall our basic formula that XD is equal to FW prime times TD. And remember, we had a method to develop that water saturation versus XD plot. Something that looks like this at different times. Our algorithm kind of worked as follows. We would choose a dimensionless time to make the plot, TD. So we got one thing in there. Then we would choose a saturation, SW. Okay, has to obviously be between 0 and 1, but really you want it greater than SWI and less than 1 minus SOR. But you choose a saturation. At that saturation, you determine FW prime. We have plots of that, right? I'll show it again. We got a plot of FW prime. So at a given saturation, you can calculate FW prime. Then you multiply that FW prime, and you get XD. So it's sort of like an inverse function, right? SW is on the y-axis and XD is on the x-axis. And so what you're actually doing is you're inputting the y-axis value, SW, which goes into FW prime, and you produce the x-axis value. That's sort of opposite than probably all the plotting that you've ever done in your life, right? Like I give you a function, y is some function of x. You plug in x, you calculate y. You plug in x, you calculate y. What we're really doing now is that we're plugging in y and we're calculating x. And that's a little bit more complicated, but it works fine. There is a little problem though. My plot of FW prime versus SW, as we've seen, looks something like this, right? It goes through a maximum. So this curve goes through a maximum, which means that for a given FW prime, there are two saturations which correspond to that. So there's two saturations which correspond to the same FW prime. And because of that, if I went through the process I just explained, you would get a plot that looks something like this. This is SW. This is the distance, dimensionless distance along the reservoir. This is 1 minus SOR. The water saturation would start to decrease. Well, that makes sense. But you would continue to make your plot. It would look like this. This is SWI. So at a given position, you actually have three saturations. Two of the saturations correspond to what was on this plot. The last one is the irreducible water saturation. We call that a triple point saturation, and it makes absolutely no physical sense. None. You can't have, in a 1D reservoir, 2 or 3 saturations at the same location. Right? If this is in 1D, and I wanted to say at a dimensionless distance of 0.5, so halfway along the reservoir, the saturation is one value. The saturation of that location is one value. You can't have 3 locations. So this is non-physical. It doesn't make sense. What should actually happen is at some saturation, again I'm going to call this SWF, we have that shock front. So what the real curve should look like should be something like that. I don't think I made them completely parallel, but you get the point. So this is the non-physical. This is, we just use math without thinking things through, and this is the physical solution. Here's my moving wall, my shock front. Remember, this is at just one time. If I were to plot it at a different time, like earlier, then maybe I would get this. This is an early time, this is a middle time, this is at a late time. Okay, and if this is 1, then when this wall, this shock front, reaches the producer well, that's my breakthrough time. So, if we can figure out what SWF is, that's no problem. No problem. If I can tell you how to calculate SWF, then you use this algorithm that I explained to plot these points up until SWF. But for after that, and I'm going to call this X location XDF. Remember, F stands for front. So XDF is the front location. SWF is the water saturation at that front location. So for any XD greater than XDF, the saturation is 0. I'm sorry, not 0, but equal to the initial water saturation. Okay, and you get these plots over here.